Okay, welcome to the final part of lecture 2. We'll talk a little bit about the outstanding issues we mentioned at the end of the last segment. Look a bit about linearity and start talking about residuals now. They'll be useful to us. Look at limit of detection, limit of quantification, talk about line est, another Excel function, and then wrap up by talking a bit about sensitivity and repeatability and reproducibility. Okay, so that's where we left off in the last segment. Starting to talk a little bit about the limitations of Rsquared, and now it can tell us things we probably need to know, such as how low we can detect, the limit of detection, limit of quantification, both of which are derived from something called residuals. Okay, here's a graph of data. The first 4 points on the line are probably linear, but the last two, probably not. Now, there are some issues with this. We would normally try to exclude these data for this simple reason. If we try to put a trend line through the full set of data, the y-axis intercept is going to be very different from what it is from the linear portion. Now, R-squared won't necessarily tell you about this. It's based on how the points are distributed on each side of the line. It's just an average of that, really. Things like residuals can give us a much more sophisticated way of looking at this. Okay, so how do we know it's linear? We can eyeball it. Does it look linear? Are all the points on the line? Again, as I mentioned, the R-squared value, even though one is a perfect straight line ostensibly, isn't necessarily the best way of doing it. Residual plots are a better way. They will find any non-random distribution of data, indicating that data is not as linear as we'd hope it was. Okay, so what are they? I'm trying to avoid statistical jargon here. I tend to think we use statistics as a tool. If you want to read about the statistics behind it, you'll find plenty of information about lines of best fit and regression lines. Trend lines, we described as y equals mx plus c. But a residual then is defined as a point. A residual for any point is a measure of the vertical difference between that point and the line of best fit. That is to say, the trend line. There's a picture here which makes that clear, I hope. The image at the top is a typical experimental results, a trend line with the data points scattered around it. But the image at the bottom is what's called a residual plot, where we've actually measured the distance between in each individual plot and the line of best fit. That's to say, the trend line. This can give us some clear visual information about what's going on with our trend lines, and we've got some examples of that coming up. Okay, so here's an example of a good trend line. The residuals for a good trend line, that is. We notice they are, broadly speaking, randomly distributed. There are ways which you can decide that, which we'll probably talk about in later lectures. But at the moment, we just look at and say, well, they appear to be randomly distributed. That's fine. Certainly compare the next examples that we're going to see. Now, if you notice this one, we start off with the residuals around 1 as being tightly clustered, but by the time we get to 9, they're much more widely scattered. Now, this is diagnostic of standard deviation increasing with concentration. So a line becomes less valid as we increase the standard concentration. Now, maybe this is one of those examples that I alluded to in the last segment, that we need to think about the concentration range, and maybe even though it still appears to be linear, we may not be able to go to higher concentrations. R-squared probably won't tell you this. Here's another one. The data is in fact a curve, and the residuals also appear to be curved as well. We start off below the line, we go above the line, and we come back down again. So again, we need to think about linearity in terms of the standards we're using. Here's another one where somebody has tried to force the intercept through 0. We saw an example of that a couple of slides back. You get this distinct line going either from, in this case, above the line down to below the line, or vice versa. There's a clear trend through them. So very often we can't force the intercept through 0. Y-axis intercept often isn't 0, because there may be some non-zero component imposed by the way we're measuring, for example. Okay, so we use Excel for residual plots. And there's an example of a calibration line, and the residual plot we've got from it. It's 24 points, so it's not that diagnostic, but it's not bad. It probably looks quite okay. Now, to use it, you need the full version of Excel. It won't work in a version of Excel on the iPad, and I'm pretty sure it doesn't work in the online version of Excel as well. But if you have the full version, and we are looking at methods for ensuring students who don't necessarily have this at home can find some way of doing this as well, so don't panic. What you need to do is follow the method that's linked there. Load the analysis toolpack in Excel. It's there in Excel already. You just need to tell Excel you want to use it. And then when you have a look at that, there is a video walkthrough of how to do residual plots in Excel. Okay, so here's an example. I created some data. The first few points up until the last three are a straight line, more or less, whereas the last three are curving. And we'll notice when we do the residual response plot in this case, we get a distinct curve, and it's very diagnostic. So we can say these data are curved, they aren't following a straight line law. So we can't use y equals mx plus c and derived versions of that to calculate concentration of samples, for example. Okay, so there's a tutorial exercise in the Excel spreadsheet that's mentioned at the bottom, which will be in the notes. Just basically walks you through how, ask you to do some residuals for these particular data here. Okay, limited detection, limited quantification. I mentioned a couple of times, it's difficult to analyse down to effectively zero. All systems have random noise in them. Modern instrumental systems have very, very low amounts of noise, but there's still a point where we can't analyse below a certain level. This next graph sort of summarises all of this. We've got the straight line portion now, which we've designated as both, in this case, both the linear interval and the measuring interval. They happen to coincide here. Sometimes they don't necessarily, but in this case we're assuming they are. And right at the bottom of both of them we have LOQ, the limit of quantification. That's how far we can go down while still having our data within the valid straight line. We can actually detect our samples down to the limit of detection, but we can't do that quantitatively. Some analysts, that may be useful just to find out if something's there. But from our points of view, I guess we're mostly interested in can we quantify things consistently, accurately. Okay, so there's some definitions using the graph on the previous page, and these, if this sort of thing came up in an exam, this is the sort of thing you would use for your answer. I'm not going to read them out. You can read them out in your own time. And we'll move on to doing calculations on these. Okay, so here are the two equations which allow us to do LOD and LOQ. They contain the variable m, which is the slope, which we're familiar with, but also this thing SR, the standard deviation of the residuals. So you take all your residuals in a set of data and you get their standard deviation. Now Excel will do this for you, which we'll by the method we'll see in a minute. Yeah, so I've got a video there of how to do it. You use a function called lineest, which is one of Excel's statistical functions. Again, I'm pretty sure this won't work on the iPad. It might possibly work in the online version, but I'm not entirely sure, but it'll definitely work, of course, in the full version of Excel. It's an interesting function. It's one of Excel's array functions, so there's a certain amount of magical hand waving you have to do to get it to work, but it's all explained in the video. There's a tutorial exercise associated with this, using lineest to derive the standard deviation of the residuals and then do some calculations based on those data. Okay, so sensitivity. Again, something you might want to consider reporting, and this is very easy. What it is a change in detector response. Now, we see the triangle there, that's delta, the Greek letter. Delta R is change in response, and delta C is change in concentration. So it's the change of detector response or the change in concentration, which is, of course, just the slope of the line. So that's quite easy to report. Now, why does it matter? It matters in experimental design. Here's three possible lines. If you look at line 1, we get a big response. A small amount of our analyte produces a big change in the detector response, but unfortunately it only does it over a relatively small concentration range. Conversely, if you look at line 3, we don't get much of a response change, but we get a big concentration range. Now the problem with both of these is they do produce quite a lot of errors in the data. What we actually want is one that's in the middle, line 2 in this case. So it produces a good response over a reasonable concentration range. Now, we design experiments in labs to do this, but if you're doing a method, finally a project, for example, which involves method development, this may be one of the things you want to look at. Increasing sensitivity, we see there, is obviously a good thing in some circumstances, but generally speaking, we're looking for good sensitivity over a good concentration range. Okay, to wrap up this section, a little bit of a talk about repeatability and reproducibility, which are things you need to consider in a sort of thought experiment sense for things like doing critical analysis of your experiments. When you do critical analysis of experiments, and especially your final year projects, whatever it is you do in your final project, you always need to think about the limitations of what you've done and how you can improve it. Now, thinking about repeatability and reproducibility, which are defined there, is one of the ways you can do this. We'll talk about some possibilities on the next slide. So there's a couple of definitions there. Broadly speaking, repeatability is something you might do yourself. Reproducibility is possibly something other people might do, but there are sort of other definitions as well, which you can look up. So repeatability, done in the same lab, by the same experiment, using the same method. So you've done your analysis on whatever it is, then you've repeated it. If you change any of them, you're imposing reproducibility. Now, it may be being done in a different lab, a different student might be doing it, or you might be doing a different method. Using different methods is obviously a very powerful way of doing this, because methods do give different results for food, and food, as we discussed, is very heterogeneous. So in critical analysis, you would talk about how you might improve the method by perhaps using different methods, perhaps using bigger samples, lots of things you can potentially do. Right, okay, that's it for lecture 2. Thanks for listening.